We're going to do some more practice on this video with differential equations and try to solve a few of them or determine if they are solutions. So our first problem is to determine if this y equals cosine 2x is a solution to the differential equation y to the fourth, or the fourth derivative of y minus 16y equals 0. So we're going to need to know what the fourth derivative is. So we'll start with the first derivative. So our first derivative, y prime, is going to be, we're going to get 3. The derivative of cosine is a negative sign. And then from the chain rule, we're going to get an extra 2. So that means our first derivative is going to be a negative 6 sine of 2x. Then its derivative, our second derivative, we're going to get a negative 6. The derivative of sine is a cosine of 2x. And we're going to get another 2 from the chain rule. And so that's going to be a negative 12 cosine of 2x. So our third derivative will be, we'll get our negative 12. The derivative of cosine is a negative sign. We get another 2x and then another 2 from the chain rule. So we're up to 24 sine of 2x. Did I do that right? So you have negative 3, negative 6, 12. And finally, our fourth derivative, we're going to get our 24 times the derivative of sine is going to be a cosine 2x. And from the chain rule times another 2. So that's going to look like 48 cosine of 2x. So now we'll come over to our differential equation and we'll see if this is going to work. So we plug in the fourth derivative, that's 48 cosine of 2x minus 16 times our original function y, which is 3 cosine 2x. And the question is that in fact equal to 0? So that's going to get us to 48 cosine 2x, since 16 times 3 is 48. And we're going to see that that is in fact equal to 0. So yes, our function is a solution. Okay, so here's a little bit different twist on this. So we're going to first verify that 2x squared minus y squared equals c is the general solution to y prime minus 2x equals 0. And then we're going to try to find the particular solution that contains the point 34. So our differential equation is going to require us to know what y prime is. So what we can do here is a little bit of implicit differentiation. So we're going to solve for our y prime, but not just try to get y by itself right off the bat. I think it's going to be a little easier to do implicit differentiation. So the derivative of 2x squared is going to be 4x. We're going to get a minus 2y to the first times y prime, and the derivative of a constant is 0. So we will try to solve for y prime. So I'm going to add the 2y prime to the other side, and then get y prime and divide that 2y to the other side to get 2x over y. So there is our y prime. I'm going to just write it down here. Y prime is 2x over y. So now we're going to come to our differential equation, and we're going to get y times our y prime, which is 2x over y, minus 2x is equal to 0. We can see that these y's will cancel, and that will get us to 2x minus 2x equals 0, which it is. So we have satisfied part A. We've shown that that's the general solution because it satisfies the differential equation. So now we're going to come back to our 2x squared minus y squared equals c, and we're going to plug in the 3 for the x and the 4 for the y and see what that gives us for c. So 3 squared is 9, times 2 is 18, minus 16. Looks like c is going to be 2. So our particular solution is going to be 2x squared minus 3y squared is equal to 2. In general, what we would expect here is to get y by itself and solve for y. So if we do that, we're going to get a negative y squared is going to be a negative 2x squared plus 2. We can divide through by negative 1, and that'll be 2x squared minus 2. We will square root both sides and initially get a positive and a negative. Square root of 2x squared minus 2. Now we can't keep both the positive and negative, or it's not a function, since our initial condition had a positive value for y. That will inform us that we need to keep the positive square root of 2x squared minus 2. So there's our solution. So remember, a solution to a differential equation has to be a function. Okay, so we will now try to find the general solution for a couple of differential equations. So we can, in this case, we normally try to separate the variables. We can, in this case, just go right to integrating both sides since there are no y's. So this is sometimes referred to as an exact differential equation. So the derivative of the integral, rather, of dy dx is y. And on the other side, we're going to need a u substitution. So I think we can say u is 5 minus x. That's going to give us du is just dx, or 1. And so that will get us to x times the square root of u du. But we have to get that x in terms of u. So coming back to our u substitution, if I add the x to the left and subtract the u to the right, we see that we can replace that x by the 5 minus u. I'm going to think of the square root of u as being u to the 1/2. Then distribute, and we will get 5u to the 1/2 minus u. We're going to add exponents and get 3/2. So now we can use our power rule. So we're going to add 1 to the 1/2 to get 3/2. We're going to have a 2/3 that's going to multiply that 5. We're going to add 1 to the 3/2 to get 5/2 and put that reciprocal 2/3 in front. So going back with a little cleanup and going back to our original x's, that's going to be 10/3 times our 5 minus x to the 3/2 power minus 2/3 times 5 minus x to the 5/2 power, and then plus c is our constant of integration. Okay, on to the second one. We're going to, again, this is just an exact differential equation. We can integrate both sides, or it might be easier to think of as pulling that 5 on the outside. So we're going to get y equals, we're going to have our 5, and you can do this maybe without a u substitution, but if you need to, we're going to think of that as a negative 1/2 x. So we'll get a negative 1/2 dx, making dx equal to 2 du. So we're going to get a negative 2 e to the u du. And so that's going to get us to negative 10. Integral of e to the u is e to the u. So we're going to get that same exponential and then our constant of integration. So those are mostly just integration problems there. Now we'll get to some more interesting ones. So ones where we really have to separate the variables. So here we have our differential equation. dy dx is x squared plus 2 over 3y squared. And we have the initial condition 0, negative 2. So to separate the variables, I'm going to multiply the 3y squared to the left side to join the dy, and multiply the dx to the right side to join that x squared plus 2. Now, there's a kind of decision you make here. Do you want to bring that 3 to the left side In general, we want to keep the y side as uncluttered as possible because eventually we're going to have to solve for y. But in this case, if we think ahead a little bit, bringing the 3 with it is going to make that integral work out even cleaner. So I'm going to bring the 3 with the y squared to that side because that's going to make that integral be just a nice y to the 3rd. On the other side, we're going to get 1/3 x squared plus 2x and then plus c, our constant of integration. Now at some point we need to use our initial condition and also completely solve for y. In this case, I think it's probably easier to use the initial condition now before we take the cube root of both sides. So I'm going to plug in the -2 for the y and the 0 for the x and get that c is going to be -8. So that is going to make our equation so far look like now y to the 3rd is 1/3 x to the, so that should be x cubed. Sorry about that. So I got the coefficient right, but not the power. So it should be 1/3 x cubed. And then we have our plus 2x. And now we've figured out the constant is a -8. We need to go one more step and take the cube root of both sides. And so it's not going to be too pretty, but we're going to get 1/3, the cube root of 1/3 x cubed plus 2x minus 8. And that is our particular solution to the differential equation. Okay, let's look at another one. So here's our differential equation. Now this is, sometimes you'll see the derivative written as a y prime instead of a dy dx. We still want to separate the variables, so it may be more clear to rewrite the y prime as dy dx. It's your call. You can do it either way. So we do have to separate the variables. So in this case, I'm going to bring the y to the left side, but I'm going to leave that constant 3 behind because looking ahead, I just want to keep that y side as uncluttered as possible. So the 3 is going to stay on the right side, and we're going to divide that 2 plus x to the right side and multiply the dx as well. So here's what our expression looks like, our equation looks like, once we have separated the variables. Now we can integrate both sides. So we're going to get the natural log of the absolute value of y. And you can see, hopefully, that that right side is going to be a 3 times the natural log of the absolute value of 2 plus x, and then plus c. Now, I would not recommend plugging in the initial condition just yet. I think it's a lot harder to solve for, although this one's going to be pretty tricky anyway. So what we want to do is to exponentiate both sides, but we're not really ready to do that on the right yet until we do a little work. We don't want this 3 getting in the way of the natural logarithm, so we can use our property of logarithms to bring that into our logarithm as an exponent. So it's going to look like the natural log of the absolute value of y is equal to the natural log of 2 plus x to the 3rd, and then there's our plus c. Now we can exponentiate both sides, and we'll get out of those logarithms, and so we'll get the y. Now we don't have to worry about the absolute value because what we're going to get here, the e to the natural log is going to make that be a 2 plus x to the 3rd, but then that c is going to become a coefficient in front. So if you want to see what that looks like, that's going to be e to the natural log of 2 plus x cubed times e to the c, and we're just going to say that's some constant, and this exponential with a logarithm that are inverses of each other will cancel, getting to the constant c times 2 plus x to the 3rd. So now we're ready for our initial condition. So we can plug in -5 for the y, and we're going to get c times, and we're going to get 2 plus negative 2 to the third, and so that is going to be a problem. So that's not going to work. We can't get negative 5 equals c times 0 to be meaningful. So that means I goofed up when I wrote this. I'm going to fix it right now. This is what we can do when you're making up the problem. So I'm going to change that from a negative 2 to a negative 1. So that's going to be a negative 1. So that's going to change then this to being a negative, I don't know what it's doing there. I'm going to change that to a negative 1. And so that will now make, we're going to get 1 cubed is 1. So we're going to get just, I don't know why it keeps doing that flashing there. That's weird. So we're going to get that our c is a negative 5. So that is going to make our equation y equal to a negative 5 times 2 plus x to the third. So I had to adjust that initial condition on the fly there. Okay. All right. Let's try another one. So here we have capital T and little t. Capital T is our function. Think of it maybe like temperature, and little t is our independent variable. You can think of that like being time. So we're going to first add this term to the other side. So we're going to get d capital T is going to be a 0.2 times 50 minus capital T d little t. Now we're going to divide this expression with the capital T in it to the other side, but I'm going to leave the 0.2 on the dt side. And we have to bring the 50 with it, the 50 minus t, together as one quantity. So we're going to divide all of that to the left side, leaving the 0.2 and the dt on the right side. Now we can integrate both sides. We have to be careful on this left side because I'm just going to write out real quick our u substitution. And you can try to do this in your head, but just be careful because you're going to get an extra negative sign there that's going to be really important to be aware of. So our d capital T is going to be a negative du. So our integral is going to become a negative du over u on the left side, which is going to become a negative natural log of u. And so I'm going to come up here with it and call that a negative natural log of the absolute value of 50 minus t. Now on the other side is pretty straightforward. We're integrating 0.2 with respect to little t, so we're going to get 0.2t plus our constant of integration. Now at this point, it's going to be way easier to deal with this negative sign right now than to try to bring it into the logarithm as an exponent. So I'm going to multiply through by negative 1 before we try to exponentiate both sides, and I would say before we try to use our initial condition. So with these logarithms, I think it's easier to exponentiate both sides first and then come back and use our initial condition. So e to the logarithm is going to cancel, and we're going to get 50 minus t. As we've seen before, this right side now is going to be c e to the negative 0.2t. Now just notice, if we hadn't caught that negative sign correctly and dealt with it as we did here, we wouldn't get the coefficient on the exponent to be correct. So it's kind of an important step. Now I'm going to plug in 30 for the t, capital T, and 0 for the little t. So that'll make it be 50 minus 30 is equal to c e to the 0. So that's going to tell us that c is 20. So that's going to get us to 50 minus capital T is going to now be 20 e to the negative 0.2t. Remember, we still have to solve for t, capital T. So I'm going to bring the capital T to the right side, adding it, and subtract the 50 to the other side. So it will look like, I believe, we're going to get capital T is equal to negative 50 plus 20 e to the negative 0.2t. Okay? All right, I think that's it for this one. Very good.